This presentation is about the molecular orbital theory of three species with triple bonds. Below is the Lewis diagram for the dinitrogen molecule. The Lewis diagram predicts a triple bond between the two nitrogens, and in this Lewis diagram, both the octet rule and the total valence electron number is adhered to, as there is 10 valence electrons on both sides of the arrow on the diagram, and there's 8 outer electrons on the right side of the diagram. This is the molecular orbital diagram for dinitrogen. All shells have been included, not just the valence electron shells. Each nitrogen has a 1s2, 2s2, 2p3 electron configuration. The shells fill according to Hund's rule. This is shown on the 2p orbitals, where the shells will half fill before they add a second electron and fully fill. When the orbitals are mixed and become molecular dinitrogen orbitals, there are antibonding and bonding shells. The asterisk on the diagram denotes the antibonding orbitals. Antibonding orbitals are where the symmetry of the orbital's charge is not in phase, so two positive lobes are not overlapping and not facing each other, as shown on the right of the slide. Bonding orbitals are where the lobe charges can overlap and are on the same side, as shown on the right. The configuration for the dinitrogen molecule is shown at the bottom underneath. It has 10 bonding electrons and 4 antibonding electrons. The equation to work out the bond order is bonding electrons minus antibonding electrons divided by 2. So when you work this out, it has a bond order of 3, which shows a triple bond, as a bond order of 1 is a single bond, a bond order of 2 is a double bond, etc. Although the dinitrogen has 3 pairs of electrons and they are all in bonding p orbitals, this is also significant of a triple bond, as it is 3 pairs of electrons shared between two molecules, atoms. This is the molecular orbital diagram for carbon monoxide. The carbon has a 1s2, 2s2, 2p2 electron configuration, and the oxygen has a 1s2, 2s2, 2p4 electronic configuration. The oxygen's orbitals are lower down on the diagram than the carbon's. This is due to the oxygen's electronegativity compared to the carbon. The oxygen has a higher affinity for electrons, so the bonding orbitals get pulled closer in energy to the oxygen, and the antibonding orbitals go closer to the carbon. This is not the same in N2, as both atoms have the same electronegativity. The other difference in CO2, the N2, is the sigma 2p orbital is lower on the CO, as the oxygen has enough protons in its nucleus to interfere with the sp orbital mixing. This causes the sigma 2p to drop in energy and the pi 2p's to rise in energy due to attraction to the positive nucleus of the oxygen. The O22 plus cation has the same amount of electrons as the dinitrogen molecule, which means they are isoelectric. As both N and O have a 1s2, 2s2, 2p3 electron configuration, they fill the same orbitals. But on the O22 plus cation molecular orbital diagram, the sigma 2p is lower, as explained in the last slide. When working out the bond order, the O22 plus cation has a bond order of 3. So by removing 2 electrons from the O2 molecule, 2 electrons were removed from antibonding orbitals, as the 2 extra electrons can't go into the full 3 bonding p orbitals. So when you calculate the bond order, there is a smaller number taken away from the same number. So the bond order increases from 2 to 3.